This video is brought to you by electricalexamcoach.com, offering the #1 electrical exam prep series. You can take our paid version with the Unlimited Testing Center, but you can also take our free version that is completely free without the Unlimited Testing Center. Also, if these videos have been helping you at any time, you can also go there and pay it forward to see it head on to the next generation. I am the Electrical Code Coach. Let's go ahead and get to it. What's up? It's the Electrical Code Coach, and this is week 2 of the Electrical Code Coach training program. This week, we're going to be diving into Ohm's Law and intro into load calculations. If you ever need anything from me, you can email me at electricalcodecoach@gmail.com. Let's get to it. Okay, so I like to start out my in-person classes with some icebreakers. This week's icebreakers were, if you could be a superhero, who would it be? And what is one area of your personal life that you want to improve in? Now, if you're watching this video and you didn't take the class in person and you're watching it online, you can drop it in the comments below. Let's get to it. All right, y'all, I'm super excited about this week's video. This week, we're going to be learning about Ohm's Law. So we're going to start off in Ohm's Law, and we're going to lead right into load calculations. Super excited about it. So how many of you have heard about Ohm's Law? Ohm's Law was discovered by Georg Ohm. And the relationship states that the potential difference, voltage, across an ideal conductor is proportional to the current through it. The constant of proportionality is called the resistance. Ohm's law is given by this equation, E equals IR, where E is the potential difference between 2 points, which include a resistor. Now that sounds like a whole bunch going on there. We're going to break it down piece by piece. This is a very integral part to you learning and getting your electrical license and just being a well-rounded electrician. So don't be overwhelmed by it. We break it down step by step, and by the end of this lesson, you'll be a pro at it. Let's get to it. This is the Ohm's Law pyramid, and we're going to talk about it more here in just a second. All right, so this is the Ohm's Law period. It's also an easy way to remember the Ohm's Law formula. So does anyone know what the E stands for? The E stands for electromotive force, like pressure pushing on water or like gravity pulling on everything on Earth. It's what pushes and pulls the electrons to jump from one atom to the next. Electromotive force is measured in voltage. Now, if you are an engineer and you're taking my program, you guys may use the V on your plans and on your calculations. But in the tools on electrical world, when it comes to getting your electrical license, we use E to represent voltage in our relationship. So as you remember, as we're dealing with these problems, remember that the E stands for voltage. All right, so does anyone know what the I stands for? Electrical current is the quantity of electrons passing through a given point in an electrical circuit, like the number of cubic meters of water that go over the falls in a second. An electrical current is measured in amperage, or amps for short. So remember in this relationship that I stands for amps. So our E stands for voltage, and our I stands for amps. All right, does anyone know what the R stands for? The electrical resistance of an object is a measure of its opposition to the flow of the electrical current, and its ease with which an electric current passes. Electrical resistance carries some conceptual parallels with the notion of mechanical friction. But just remember, as you think about this relationship of EIR for our Ohm's Law formula, just remember that the R stands for resistance. All right, let's go ahead and jump right into it. Now we're going to pull all this together. This picture that I keep showing is actually a formula, and it's an easy way to remember this relationship. So we have E, we have our voltage on top, we have our current to the bottom left hand, and we have resistance to our bottom right hand. And that's how you remember EIR. It's E over IR. And it's actually an easy way to remember this relationship. So this here represents a math formula. The E on top is on top of a division line. The I and R are implied multiplication, and we're going to learn more about what that means now. I want to note that the IR together is implied multiplication, but if it's easier, you can also write it like this, E over IR, remembering that the line below the E is a division line, okay, and the I and the R smushed together implies multiplication, and you can also write it like this at first while you're getting used to it. If you know any two of the equation, you can always find the unknown. Okay, so we have a 120 volt circuit with a 10 amp draw. What is the resistance on this circuit? Now we just learned a moment ago that if we have any of the two, then we can find the unknown. So in this case, we have 120 volts, we know our voltage, and we also know our amperage, which is I. So we know E and I. So all we have to do is plug in what we already know, and then we're going to use very basic math. So treating this like a division line, we're going to take 10 and divide it up into 120, and that's going to let us know what our resistance is. So we take and bear that math out. We take and divide 10 up into 120, and that lets us know that our resistance is 12. So we have a 12 ohm resistance, and we have 120 volts, and we have 10 amps of draw. And what we did is we plugged in the two knowns, and we solved the math problem. So this is a division line. We took 10 up into 120, and that gives us a resistance of 12. Great job. And this is a very simple way to look at it. So any one that you don't know, you just cross it out, plug in the two that you do, and follow the appropriate math problem. And we're going to go through it one step at a time. Okay, so let's say we have a 120 volt circuit with 12 ohms of resistance. What is the amp draw on this circuit? So what we do is we just plug in what we do know. We know that there's 120 volts, and we know that there's 12 ohms of resistance, and we're trying to solve for I. So we just take our 12, divide it up into 120, and that's going to let us know what our current is. And in this case, after we bear the math out, we're going to find that the current is 10. You see how that relationship works? It works back and forth. As long as I know any of the two, I can always find out the unknown. Great job. All right, let's do another one. What if we have a circuit with 10 amps on it and 12 ohms of resistance? What is the voltage? So the letters together imply multiplication, but if it's easier for you, you can write it like this. So we take our knowns. We know the amperage and we know the resistance, and we're trying to solve for voltage. So what we're going to do is we're just going to multiply. We take our 10 amps and we multiply it by our 12 ohms of resistance, and that's going to give us our unknown. So we take 10 multiplied by 12, and that lets us know that we have 120 volts. So E equals 120. Do you see how this relationship is coming together? As long as you understand that this is a multiplication problem and this is a division problem, you can always find your unknown. All right, let's go ahead and do some practice. So let's see if we can solve this one. We have 120 volts on top, and we have 12 ohms of resistance, and we're trying to solve for a current. So what we would do if you wanted to break out your calculator is you would break your calculator out, and what you would do is first you would put the 120, and then you divide it by 12, and that's going to let you know that you have 10 amps in this scenario. Let's go ahead and do another one. So we have 120 volts, we have 10 amps, and we're trying to solve for R. So what we do is we take our 120 and we divide it by 10, and that's going to let us know that we have 12 ohms of resistance. Let's go ahead and do it for voltage. We have 10 amps, 12 ohms. We just take and multiply it out. So 10 multiplied by 12, and that's going to give us 120 volts. Great job. After you do this over and over and practice it, you're going to see that it's very intuitive, okay? It's going to become very common sense for you, and this is going to be something that you're going to be able to whip through, and if your friends don't know it, you can show your friends. All right, so let's go ahead and learn about another relationship. It's very similar, and it's P equals IE. So we know that I equals amps, and we know that E equals voltage. So this equation is saying that I times E equals P. But what does the P stand for? Well, P stands for electric power. And electric power is the rate of energy consumption in an electrical circuit. The electric power is measured in units of watts. So P equals watts. So if you had 75 watts, it equals 75P. And if you take a look at both of these pyramids, you can see that they are very simple and easy to use. This one is the original Ohm's law, E equals IR. And then if you take a look at this one here, it's another very similar one. But you put P on top, you put I down in the bottom left-hand corner, and you put the voltage over here. So if you know any of these two, you can find out the unknown, and we're going to practice it now. All right, y'all, let's go ahead and do some practice. So we have a 1200 watt load on a 120 volt circuit. What will the amp draw be? So what we do is we lay out our pyramid and we plug in what we know. We know that we have 1200 watts and we put it on top. And we know that we have 120 volts and we're solving for the current. So what we do is we take our 1200 watts and we divide it by 120, and that's going to give us a 10 amp draw on this circuit. All right, so let's say we have 1200 watts with a 10 amp draw. What is the voltage? Same thing, you always lay your problems out in the pyramid style. So we put 1200 on top, we put our known current, and we're trying to solve for voltage. We just take 1200 divided by 10, and that equals 120. Now we go ahead and do it for our next one, 120 volt circuit with a 10 amp draw. What will the wattage be? So remember, we used our implied multiplication. Just plug in what you know. We know the amperage and we also know the voltage, and we're looking for the wattage. So we just multiply that out. We take 10 multiplied by 120, and that's going to equal 1200 watts. And this is a very simple way to remember both of them. This is going to be a super important part, not only for your testing, but in your well-rounded electrical career. Let's get to it. All right, y'all, so let's keep practicing. I'm actually going to have you do this one on your own. Just remember, plug in what you know and then try to solve it yourself. So we have a 240 volt circuit with a 9 amp draw. What is our total wattage? I want you to pause the video now and see if you can solve this one for yourself. All right, well, hopefully you took and you drew your pyramid and you put P on top and you plugged in your two knowns. So we take 9 multiplied by 240, and that's going to give us 2,160 watts. Remember, you can use this relationship anytime. Great job. All right, so let's keep practicing with Ohm's law. So we have a 120 volt circuit, 12 ohms of resistance, and we're solving for I. What would we do? That's right, we're going to take 120 and we're going to divide it by 12, and that's going to give us 10. We take 120 volts and we have 10 amps on it, and we're solving for R. So what do? We take our 120, we divide by 10, and that's going to give us 12. We take our 10 amps and we have 12 ohms of resistance. We're going to multiply those two together, and it's going to give us 120 volts. Great job. All right, so let's practice with power. We have 1200 watts and 120 volts, and we're solving for I. And we just take 1200 divided by 120, and that's going to give us 10. We have 1200 watts, and we have 10 amps. We're going to take 1200 watts, we're going to divide it by 10, and that's going to give us 120 volts. And we have 10 amps, and we have 120 volts, and we're trying to solve for P. We take and we multiply those two out, and that's going to give us 1200. Great job. Just keep practicing this. As you do it more and more, it's going to become more natural, and you'll see how often that you use it in your electrical testing and out in the electrical field. Let's get to it. All right, y'all, I'm super excited. Starting now and for the next few weeks, we're actually going to be learning how to do load calculations. Load calculations is a huge subject, so what we do is we take it and break it down piece by piece, gradually building one step on another, leading up to a whole house load calculation. And then in a few weeks from now, we're going to teach you about commercial load calculations. I'm super excited. Let's get into it. So we're going to find ourselves in Article 220. Article 220 is broken down into 5 sections. 1 is general requirements for calculations. 2 is branch circuit load calculations. 3 is feeder and service load calculations. 4 is the optional feeder and service load calculations, and you're going to understand what that means here in a few weeks. And 5 is farm load calculations. I love Article 220. It's very dense, but it's very cool how they put it all together over the last 100 years or so and got it to fit into what we have today. Let's get to it. All right, so couple of things that we have to remember. When we're doing load calculations, we're going to round our amps when we're doing load calculations. Article 220 calculations can be rounded up to the nearest whole number when they are 0.50 and above. Round down and dropped, you drop it off the calculations when it's 0.49 and below. So it's going to look something like this. If we had a calculation that was 26 multiplied by 1.25 and we came up with an answer of 32.5, we would actually round up to 33 amps. If we ran into a calculation that was 25 multiplied by 1.25 and we came up with 31.25, we're actually going to round back down to 31 amps. So if it's 0.50 and above, you're going to round up, and if it's 0.49 and below, you're going to round down. All right, so when doing Article 220 load calculations, we're going to be using nominal voltages. So even though the actual voltage may read 115 to 230 on a given system, for our calculations, we're going to be using nominal voltages. We're going to be using 120, 120/240, 120/208, etc. Okay, so we're not going to be using actual readings. We're going to be using nominal voltages. All right, so let's jump right into it. We're going to be dealing with residential, 1, 2, and multifamily dwelling units. So everything that we're getting ready to learn, although some of them universally apply over to commercial, pretty much what we're going to be dealing with the next few weeks is residential setting. So that's a single family, a two family, or a multifamily dwelling unit, each one with their own little nuances. So let's go ahead and jump into it. When we're doing general lighting and receptacle loads, we're going to be using the outside dimensions of a building. Okay, so if we take a look at this here, we're going to be using the outside dimensions of the building for our calculations. This way and this way. And we're going to learn more about that as we move through. When we're calculating general lighting and receptacle VAs, open porches and garages are not counted in our square foot VAs. We're going to learn about VAs here in just a moment, but when you are dealing with these, you're not going to count open porches and you're not going to count garages. You're only going to be counting the actual living space, okay? So you don't have to worry about that being in the square foot of your count when you're doing your load calculation. Do not count garages, open porches, carports, and spaces not adaptable for future use. That can be really hairy when you're out in the field, but your question will either say nothing and you will count it, or it will say a space that's not adaptable for future use. Now, when you're doing a load calc out in the field, you need to talk to your inspector on what they classify as not adaptable for future use. All right, so dwelling units are calculated at 3 VAs per square foot for general lighting and receptacle. Now, this is just talking about your general lighting and receptacle circuit, and it's talking about your total that you're going to calculate for your load calculation. Remember, ultimately, we're leading up to a whole house load calculation, trying to size the service, the overcurrent protection, and the wire. But first, we have to come up with what is the demand on this structure. So when you're dealing with one family, two-family, or multifamily dwelling unit, when you're dealing with the general lighting and receptacle loads, you're going to calculate that at 3 VAs per square foot. But what is a VA? Let's learn about that now. So what is a VA? So a VA is a volt amp. And for all of our questions when we're doing our testing and in the general electrical field, it's going to be equivalent to a watt, okay? Now, when you get into other areas, they may have a different opinion, but for all of your testing and when you're dealing with electrical and the electrical industry and you're dealing with all your testing, a VA and a watt are going to be equivalent. So we have 2,400 VAs, that's going to equal 2,400 watts. Pretty simple. So remember, we just learned about that P equals IE in our power pyramid, so the IE together implies the implied multiplication. So if we took a 20 amp circuit and we multiplied it by 120 volts, that's going to give us 2,400 VAs or 2,400 watts. So you'll learn all of this Ohm's law practice is going to tie directly not only into your testing, but it's going to tie directly into your in-field application of understanding watts, VAs, amps, voltage, and all these things. All right, so let's learn how to apply this. How many VAs would you calculate before demand factors? And we're going to learn about demand factors in a few minutes. First, we have to learn how to calculate the VAs themselves and figure out what our total VAs are. So how many VAs would you calculate in a home that is 1,500 square foot of living space on the main level, a 500 square foot attached garage, and a 500 square foot unfinished basement that is adaptable for future use? So we have to just kind of take our time and pick apart our question. So the first step that you do is you're going to figure out the total square feet that you're working with. So we know that we're going to use the 1,500 general square foot. We know that we need to omit the 500 square foot of attached garage. It let us know that in Article 220. Then we're going to count the 500 square foot of basement because in this question, it is adaptable for future use. So we take and add that together, 1,500 square foot plus 500 square foot, and that's going to give us 2,000 square foot. All right, in step 2, we're going to use our calculations tab and flip to Article 220. I want to take this time to get you into Article 220. So if you've used our tabs, the Mike Holt tabs, you have a calculations tab. And what that's going to do is flip you straight into Article 220. When you get into Article 220, right there at the beginning, I want you to find 220.12. And specifically, I want you to find Table 220.12. So find Table 220.12. And when you get there, you're going to notice that on the left-hand side are the list of the types of occupancies. Now, this table was pretty much untouched for a long time, but if you're in the 2020, they've changed a few things as far as the numbers go, but the layout is pretty much the same. So on the left-hand side is going to tell you the type of building, and then that second column is the volt amperes per square meter. We don't use that one here in the United States. We use the next one over, and it says volt amperes per square foot. So that's the one that we're going to be dealing with. And if you watched my How to Highlight Your Codebook video, I let you know that you might want to highlight the volt amperes per square foot so you don't accidentally pull from the wrong side. So if you look down through there, it lists a bunch of different types of occupancies. And if you look down there about a quarter way down in the 2017, it lists dwelling units. And if you slide over, it lets you know that it's 3 VAs per square foot. They changed that a little bit in the 2020. They took it out of the table and they made it its own special code. And if you look right there next to that table, somewhere in 220.14, it's going to list dwelling unit VAs, and it's still going to be 3 VAs per square foot. So they just took it out of the table and they actually incorporated it right there in the code. So you should be able to work through that and find it. Now back to our question. We had 2,000 square foot at 3 VAs per square foot. So we take our 2,000 square foot, multiply it by 3, and that's going to give us 6,000 VAs. Okay? So we're working through, and we're going to select D. Great job. Remember, it's 3 VAs per square foot, which equals 3 watts per square foot. How many VAs would you calculate before demand factors for a home that's 2,800 square foot of living space on the main level with a 500 square foot upstairs bonus room and a 500 square foot open front porch? Step 1, you're going to find your total square foot. So we know that we're going to count our 2,800 square foot of general. And we're going to count the 500 square foot bonus room. I want to note that the bonus room is a part of the general, but the question makers will put things in like this in the question to throw you off. Remember, their business is selling you tests. So they'll put things in there like a 500 square foot bonus room just to burn up some time, okay, because you're looking around, do bonus rooms count? That's just a part of the general square foot. So remember the list: garages, open porches, areas not adaptable for future use, those do not count. And if it's not listed right there in that list, then it is going to count. And we're going to omit the 500 square foot of open porch. So that's going to give us a total of 2,800 plus 500. That's going to give us a grand total of 3,300 square foot. All right, now we use our calculations tab. We're going to flip to Article 220. We know that the demand factors for lighting loads, we know that it's 3 VAs per square foot. So we take our total square foot. We're going to take it at 3 VAs per square foot. We bear that math out, and that's going to give us 9,900 VAs. And we're going to select C. Great job. How many VAs would you calculate before demand factors in a home that is 1,500 square foot of living space on the main level with a 500 square foot attached garage and 500 square foot of unfinished basement that is adaptable for future use? So the first thing that we're going to do is we're going to find out the total square foot that we're working with. We have 1,500 general. We're going to omit the 500 of the garage, but we're going to count the 500 of the basement because the question states that it's adaptable for future use. We're going to take and we're going to total those together, and that's going to give us 2,000 square foot total. Now we're going to do step 2. We're going to use our calculations tab. It's going to get us in the right section. We already know that it's 3 VAs per square foot, okay? And we're going to total that out. We take 2,000 multiplied by 3 VAs per square foot. That's going to give us 6,000 VAs. And we're going to select D. All right, now we're going to start learning how to take our general lighting total and add it to other parts of our whole house load calculation. So in this scenario, we had 2,000 square foot multiplied by 3 VAs. That's going to give us 6,000 VAs. Now we take this 6,000 and we set it aside for later. So when I'm building a whole house load calculation, I put my general VAs there at the top, and then we're going to start adding to it, and we're building a larger math calculation. I want to note that these load calculations only apply to 1 and 2 family dwelling units and multifamily dwelling units. This is not how you would approach a commercial occupancy load calculation. There's going to be different rules and regs, and we're going to learn all about them later in the program. All right, now let's learn about the small appliance and laundry circuit VAs. So in every whole dwelling unit load calculation, you will have 2 small appliance branch circuits calculated at 1,500 VAs each. These are for the kitchen small appliance circuits, and they're going to be in every single load calculation. And you're also going to have 1 laundry circuit calculated at 1,500 VAs. Now this is a minimum, and they're not going to tell you in your question that there's a kitchen and laundry. They're just going to assume that you know that, and you know to tack it onto your load calculation. Don't worry about that. We're going to be very familiar with it, and it's just going to be a habit for you to do it every single time. But every load calculation, you're going to have a minimum of 2 small appliance branch circuits, and you're going to have a minimum of 1 laundry circuit. Now, if they give you a load calculation question that says you have 4 small appliance kitchen circuits, you're going to add 1,500 VAs for each one. But typically, all we usually have to add is the total of 4,500 VAs. And we're going to work through that now. Okay, so the easiest way to do it anytime you're doing a whole dwelling unit load calculation is to first figure your square foot VAs and list them at the top over here on the side of a piece of scrap paper. So we're going to list those over there. Then we're just going to add 4,500 VAs to the list. And that's going to represent your 2 kitchen small appliance circuits and your 1 laundry circuit. And it's going to look like this. So every time you figure those 2 out, and you just go ahead and tack it on. Now we're going to start learning how to do our general appliances, our dryer, and our range, and we're just adding them in one long load calculation. Let's get to it. Now let's talk about appliance load calculations. Now when you're doing a whole house load calculation, your range and your dryer are going to be calculated separate. Also your AC and your heat are going to be calculated separate. But you have to have a way to calculate for trash compactors, dishwashers, central vac systems, and the code has made a process for that. So let's go ahead and look at this question. When doing service and feeder load calculations, and you have blank or more fixed appliances, you can apply the fixed appliance 75% rule. So let's go ahead and use our keyword and index process to solve this one. Now, depending on what year in the code book you're in, you may use a little bit different keyword and index process that we're getting ready to show, but it's the same principle and you can use the same method. So let's go ahead and jump into it. So what's the overall theme of our question? What is it talking about here? What's the core of this question? It's appliances, isn't it? So what we're going to do is we're going to head straight back to our index, and we're going to head to A in the index. So let's go ahead and do that now. Let's head to A in the index. And when you get back there, first we're going to see if there is an appliance section at all. There may not even be one. So let's look. We look in our A's. It's in alphabetical order, so we look in APP. We see apparatus, and then we see appliances. So there is a section. Now what we're going to do is look down through those keywords underneath there and see if there's anything else that ties to our question. We're talking about calculation, so let's see if there's anything in there about calculation. So we look down. In C, nothing about calculations. Let's keep going. Look down. We keep going, and we get to L, and it says load calculations. So now we know we're in the right spot in our index process. And there's several different code articles there listed under load calculations. So let's go to the first one. But what we have to do is keep our hand or a piece of paper in the back of the book, because we might have to quickly flip back. And I'm going to talk with you about how to do that process now. So first, let's keep our hand in the back of the book, and let's head to Article 220.14 first. Okay, so when we get to 220.14, we're going to start reading the black bold headings surrounding that page. So we start there at 220.14, and we've only got 2.5 to 3 minutes per question, so we've got to be very quick at this. There were several code articles listed in the back of the code book, so we have to be careful to get in there, find out if we're in the right section, flip back to the next article. It might be the third or fourth article listed until you get the right answer. So as soon as we get to 220.14, we're going to start reading those black bold headings and see if anything about appliances pops out. So we look at 220.14. It says all occupancies. We look at part A, the next black bold heading. It says specific appliances or loads, and it sends you and lets you know that it's going to be covered through the next few sections. Then we look at, it says electric dryers, then the next one says motor outlets, then the next one says luminaries or something along those lines, depending on what code cycle you're in. But what we're going to do is look at these black bold headings until something about appliances pops out. I don't see anything on this page talking about appliances. So with that being said, I'm going to flip back in the index and we're going to go to the next code article. You've only got just a few seconds, to look at each page until you feel like you're in the right section. So let's flip back. So when we flip back in our index, back under appliances, back under load calculations, we're going to go to the next available article. And in this one, it says 220.52. So we still leave our hand in the back of the index just in case we have to come back. We flip over, we find 220.52, and we quickly start reading the black bold headings to see if there's anything about appliances. So 220.52 says small appliance and laundry circuits. Well, we just learned about that, so we keep going. We go down and the next black bold heading is small appliance circuit load. We know that. We go down to the next one, it says laundry circuit load. And then the one right after that says appliance load. Okay, now I feel like I'm in the right section. So we went from appliances to load calculations, and now we've honed in on a black bold heading that's talking specifically about appliances. And that's what we do. We use the keyword and index process until we find an area with the black bold headings that we really feel like we're in the right section, and then we can start reading some of the paragraphs that are listed underneath the black bold headings. So when we get to 220.53, it says appliance load. We look down. It shall be permissible to apply demand factor of 75% to a rating of 4 or more appliances. So now it's almost word for word what's in our question here. And we look, we find out that our answer is 4. So when we're sizing and doing service and feeder load calculations, and there are 4 or more appliances, we can apply the 75% rule. And what that is that is called the demand factor. And we're going to learn all about demand factors in the weeks to come. Let's get to it. Let's do another one. How many VAs would you calculate for a single family dwelling that has the following appliances? A 4200 VA water heater, a 1000 VA disposal, and an 1100 VA dishwasher. I'm going to let you pause the video now and see if you can work this one out on your own. All right, so if you've worked this out and you remember the appliance 4 or more 75% demand factor rule, that'll save you from having to look it up. This is something that you're just going to commit to memory. And one thing I do want to know is that everything that we're learning this week and next week, until we get to what's called the optional method, is all called the standard method. So this is the standard method for doing load calculations. There are 2 methods, the standard method and the optional method, and we're going to cover both of them in this program. In this case, in our question today, if you didn't get tricked, we only have 3 appliances, so we're not going to do the 4 and 75% rule. It doesn't apply, so all we have to do is add them together. So we take 4,200 plus 1,000 plus 1,100. That's going to give us 6,300 VAs. So if you were in someone's home doing a load calculation and they had these appliances and you didn't have 4 or more, you would just do the straight math, and that would be the demand that you were adding to your service, your whole service load calculation. Okay, so working back through it, we worked out the math, we selected B. Now I do want to note that one of your choices, if you look up here at choice C, one of your choices was actually as if you had applied the 75% rule. And the test makers love to do things like this. They love to add in one of the answers as if you did a step that you didn't need to do, or if you forgot one of the steps before you got to the end. Remember, their business is selling you tests. All right, and this is a little graphic explaining what we just learned. We had our water heater, our disposal, and our dishwasher, and there's no demand factor on 3 appliances. So the 75% rule doesn't apply. Just want to let you guys know, if you ever want to use any of my slides for teaching or educating, they are all absolutely free to use. Just email me at electricalcodecoach@gmail.com. Okay, let's do another one. How many VAs would you calculate for a single-family dwelling in Dallas, Texas that has the following appliances? A 4200 VA main water heater, a 3500 VA additional water heater for the basement, a 1000 VA disposal, and an 1100 VA dishwasher. So if we've committed to memory the 4 or more appliance rule, then we do not have to work through the index and keyword process again. But if you ever forget, you would just pick apart the question and repeat the keyword and index process. And you can use that for anything in the code book. Okay, so first thing that we have to do is bear the original math out. So we take our 4200, our 3500, our 1000, and our 1100, and we total them all together. Now we can apply the 4 or more 75% rule. And this is the first time in our program where we've actually applied a demand factor. Now what a demand factor is, whether you are decreasing the demand on the service or on the calculation, or you are increasing it, they're all called demand factors. Whether you are doing 1.25 to increase the demand, or you are doing a under 1, you are decreasing the demand. So anytime you do it, you just turn it into a decimal. So 75% would be 0.75 because it's under 1. Okay, so you take your original total of 9,800, you're going to multiply that by 0.75, and that's going to give you a new reduced load of 7,350 VAs. So when you're sizing your wire, your overcurrent protection, and your overall service, they're saying that, hey, they're probably not going to turn on all these appliances at the same time. So we're going to allow a reduced load, okay, on that system, assuming that they're not going to turn all 4 of these appliances on at the same time. And we're going to let them do a smaller VA calculation for their overall service, feeder, or just general load calculation. And we're going to select C. Great job. All right, y'all, that's it for this week. So you can head over to electricalexamcoach.com and you can work through the program with the practice test, or you can do the free version that's without the practice test. I just want to see you guys win. And I want you guys to know, whether you ever sign up for any of our programs or purchase anything from any of our websites, I am here and dedicated to help you become everything that you can be in life and in the electrical industry, and it's absolutely for free. You can email me anytime at electricalcodecoach@gmail.com. I just want to see you win, and I'll help you in any way that I can. Let's get to it.